Alright, so here's another example of revolving a region around a vertical axis. And so the problem says find the volume of the solid formed by revolving the region in the first quadrant bounded by y equals x squared and y equals x cubed about the line x equals -5. I would suggest that you go ahead and stop the video now and try this on your own, see how far you can get. Hopefully you can get through all of it, and then you can just come back and check your solution. That's the best way to practice. So practice, practice, practice. Alright, so let's go ahead and figure how this would work. Not the greatest picture in the world, but y equals x squared and y equals x cubed intersect in the first quadrant at the point 1, 1 and 0, 0, of course. And so this is the region, the enclosed region that we're going to be revolving around x equals -5. Now, just so we're clear, between 0 and 1, the cubic graph is lower than the quadratic graph. So this is our x cubed graph here, and this one up here is the x squared graph. They switch when x gets greater than 1, but between 0 and 1, x cubed is lower than x squared. Alright, so let's add, and my scale isn't going to be drawn very well. The vertical axis of x equals -5 out over here clearly is not scaled correctly where the 1 is located in the first quadrant, but I just need it so you guys can see what's going on here. It doesn't have to be perfectly aligned at the moment. So this is our vertical axis we're revolving around, and let's go ahead and create our little rectangular slice like we normally would here. Not very well drawn, but I think the point will be made just fine. Of course, since we're slicing it this way and revolving around a vertical axis, we're going to have a delta y in this direction here. We want to identify our inner and outer radii. I think it would be fairly easy to see that we're going to have a washer that's going to be formed because the closer edge of the rectangle to the axis of rotation is not adjacent to or joined to the axis of rotation. So we're going to have a piece in the middle deleted. So this is going to be a washer. Our outer radius is going to be from the -5 all the way to here. I don't like how that came out. All the way to here. Okay, and we can see that's given by the cubic graph. And then our inner radius, which is here, is given by the x squared graph. And so we just got to figure out those lengths. Now remember, since we're integrating with respect to y, hence the delta y, we need to rewrite our equations in terms of solving for x in terms of y. So as we've done before a couple times, with y equals x squared and being in the first quadrant, we're going to have x is equal to the square root of y. And similarly, for y equals x cubed, we're going to have x is equal to the cube root of y. And so for our outer radius, we're going to have right minus left. Remember, horizontal length, or length horizontally in the xy plane is always right minus left, because the principle is greater minus lesser, and in the xy plane from right to left, right is greater than left. So this is going to be the cube root of y minus -5 for our outer radius, and for the inner radius it's going to be the square root of y minus -5. Alright, so now that we have our inner and outer radii, we can go ahead and set up the area of the cross-sectional slice, the area of the washer. And remember, that's always pi times the difference between the squares of the radii. So we're going to have the outer radius first, minus the squared, minus the inner radius squared. Just going back to the picture, our outer radius is going to be the cube root of y plus 5. So we're going to have the cube root of y plus 5 quantity squared minus the square root of y plus 5 quantity squared. And there's our area of our cross-sectional slice. The last thing we need to remember to do is before writing the volume integral is to figure our upper and lower limits of integration. Keep in mind that we're integrating with respect to y, so along the y-axis, and so we're looking along the length vertically here, and so we're going to be going from the x-axis, which is y equals 0, all the way up to the point of intersection here, which has a y value of 1. So the volume is going to be the definite integral from 0 to 1 of this cross-sectional area, pi times this quantity cube root of y plus 5 squared minus square root of y plus 5 quantity squared, and of course don't forget your dy. I'm not going to go ahead and work this out by hand. It's possible you could expand both of those terms and then simplify if possible through the subtraction, and then take the antiderivative of each term, and by the fundamental theorem plug in 1, plug in 0, subtract, and get a correct answer. Typically on the AP exam, when you have something this involved in finding the antiderivative, they're actually going to have you do this on your calculator or leave it just in terms of the integral. It'll say write an integral that represents this volume, and so you'll be stopping there. Now that's not to say that they couldn't or wouldn't have you do it. It's just historically they don't have you spend that much time doing these hand calculations here for longer involved problems. They'd rather just set it up and show that you understand how to set it up, and then from there either leave it like that or evaluate it on your calculator. Hopefully you got an answer just like that. You can get a numerical result by plugging it into the calculator, as I've mentioned. Keep practicing.